Most people have stepped right over them. Angular, slightly oily-looking stones resting in gravel beds, assumed to be broken glass or quartz chunks. Yet under the right conditions and with a trained eye, those same stones may be early signs of misidentified diamonds, missed entirely by hobbyists and even seasoned rockhounds. The value they walk away from could stretch into thousands per carat, all for one of a simple field check. The first hint is visual, but not the flashiest one. Unlike cut diamonds, rough stones don't sparkle wildly. Instead, they reflect light in a subdued but distinctive way, what gemologists call an adamantine luster. When sunlight hits a raw diamond at the right angle, the surface throws back a sharp, almost metallic glint that's easily mistaken for a piece of soda bottle. But there's a giveaway. Diamond rough, especially when octahedral, often displays clean, geometric faces rather than the jagged, curved edges typical of glass. In one documented case from southern Brazil, a man collecting quartz in a dry creek picked up what he thought was a large piece of smoky glass. He pocketed it and moved on. Weeks later, while sorting, he noticed the weight fell off, denser than expected. That single observation led to retesting and ultimately the confirmation of a 4.1 carat natural diamond with intact octahedral faces. The market value? Over $12,000, even uncut. His error wasn't in failing to test. It was assuming at a glance. Raw diamonds are heavier than they look. With a specific gravity of about 3.52, they feel unnaturally dense for their size compared to quartz 2.65 or glass / 2.4. This weight-in-hand sensation becomes one of the most reliable first impressions, especially when paired with other signals like translucency and lack of bubbles or curved fracture lines. Combine this with the environment, whether it's downstream of a known pipe or in a cratonic zone with heavy mineral concentrations, and you've got a situation worth a deeper look. But here's the rub. Not all shiny octahedrons are diamonds, and not all diamonds show perfect geometry. So, how do you move beyond intuition? How do you know when it's time to test, and when it's just clever-looking waste? That question sets the stage for our next move. Learning how to distinguish the subtle but decisive traits that divide imposters from candidates, starting with a trick of the light. The difference reveals itself in a flicker, just not the kind most people expect. While many are drawn to sparkle, the real secret lies in how light behaves on the surface of the stone. When distinguishing glass from diamond in rough form, relying on brilliance alone leads to costly mistakes. The smarter test is luster, and it's a clue you can read with your eyes in seconds. Glass reflects light in a greasy or vitreous manner. It catches the sun but diffuses it quickly with rounded reflections and soft, inconsistent gleams. Diamond, even in its raw state, throws a tighter, harder reflection. That adamantine luster gives edges a steely sharpness, almost as if the light is etched onto the surface rather than bouncing off. Viewed under direct sunlight or a headlamp at close range, this luster difference becomes pronounced, especially when compared side by side with known quartz or bottle glass. The edge geometry is another silent divider. While glass tend to fracture in irregular curves or shows clear signs of flow from molding, diamonds often feature stepped or triangular growth patterns, hallmarks of their crystallographic habit. You might see two or more flat faces converging at sharp angles, almost symmetrical, unlike any natural or artificial glass. In some cases, minute trigons, tiny triangular etchings, can be spotted with a loupe. These are nearly exclusive to natural diamond. Color is less reliable, but still worth noting. While glass can mimic a wide range of hues due to impurities or manufacturing additives, diamond rough tends to range from clear to pale yellow, brown, or gray. High saturation colors are rare in rough and often indicate dyed quartz or colored glass. If a stone shows strong green, blue, or red, it's more likely to be treated material unless other diamond traits are present. An overlooked but critical test is transparency, not clarity, but how light travels through. Many raw diamonds are translucent rather than transparent, diffusing light in a frosted haze. Glass and quartz often appear clearer, but lack the density and edge sharpness. It's this contradiction, dense but light scattering that catches experienced eyes. Still, the visual isn't enough on its own. Plenty of high-lead glass and synthetic moissanite pass the initial look test. That's why the field demands escalation, from eye to hand to instrument. But before we bring in magnets or thermal probes, it's worth asking, are we even standing in the right place? To get that answer, we need to understand where diamonds actually form and what ancient forces deliver them to where our boots touch the ground. Diamonds don't just appear anywhere. Their presence is tightly tied to ancient geological processes. And unless those processes once shaped the terrain beneath your feet, the odds are stacked heavily against any find. Understanding where to look is as vital as knowing what to look for. And it starts with the pipes, kimberlite and lamproite, the rare volcanic conduits that ferry diamonds from a mantle to the surface. These pipes don't erupt in today's landscapes. They formed deep in geological time, often hundreds of millions of years ago, and are now eroded to shallow depressions or hidden under soils and sediment. Yet their signatures persist. Cratons, stable cores of ancient continents, host nearly all known diamondiferous pipes. Southern Africa, northern Canada, parts of Siberia, Brazil, and northwest Australia all share this deep time crustal stability, making them prime candidates. Even within these zones, pipe remnants rarely lie exposed. What diamond seekers track instead are the byproducts of erosion. Over millions of years, weathering breaks down to kimberlite or lamproite, releasing the diamonds and associated indicator minerals into nearby stream systems. These streams and the gravel beds they leave behind often transport diamonds downstream, but not far. Diamonds are heavy, specific gravity 3.52, and like gold, they settle quickly when flow conditions change. That's why it bends in streams, inside meanders, and the upstream side of obstacles become critical terrain. These are natural drop zones where heavier materials accumulate when water loses velocity. Paleochannels, ancient stream paths now buried or shifted, can hold some of the richest residual material, preserved just below surface gravel. In dry regions, these might show as subtle depressions, vegetation shifts, or soil texture changes. On the ground, your job is to read that language. If the terrain sits near known or suspected pipe zones and the creek shows signs of heavy sedimentation or black sands, you're in a promising context. Satellite imagery and geologic maps help, but sometimes it's the character of the gravel that tells more. Are there ultra-heavy particles mixed with quartz and feldspar? Do magnetic sweeps light up? Before any field test even begins, terrain reading dictates whether effort is warranted. That includes assessing flood risk, sediment loads, and access legality. Because sampling a protected watershed, even for science, can carry legal penalties if done without the right documentation. So when a rough octahedron shows up in a place that shouldn't have glass, and the terrain whispers of deep time flows, it's time to escalate. But first, what's riding shotgun with that stone? The best finds are rarely alone, and the presence of certain mineral companions can upgrade a suspicion to a credible lead. The most credible clue often isn't the diamond itself. It's what surrounds it. In areas where diamonds occur naturally, they are rarely the only unusual mineral in the pan. Before you ever see a clear crystal glint, your sieve or battue might fill with garnet red grains, jet black specks, or opaque metallic flakes. These are indicator minerals, and when they appear in the right combinations, they act like fingerprints of a diamond-bearing source. Start with pyrogarnet. Unlike common red garnets found in metamorphic rocks, pyrope from kimberlitic origins tends to be chromium-rich, giving a vibrant purplish-pink tone and, under magnification, a clean translucency with few inclusions. They're typically small, under 2 millimeters, but their presence in stream concentrates often precedes diamond discoveries by kilometers. If your pan produces multiple pyrope grains in a single pass, that's an escalation trigger. Next comes ilmenite, metallic black or brownish black grains with a weak magnetic response. In diamond indicator suites, ilmenite often appears as rounded, opaque grains with slight surface luster. They may stick faintly to a neodymium magnet, allowing fast field separation from similar-looking but non-diagnostic minerals like hornblende. Magnetite may also appear, but in this context, it's a secondary sign, common in many rocks, and less directly linked to diamondiferous sources. Chromite is another key piece. True kimberlitic chromite tend to be denser, opaque, and deeply black, but not as reflective as ilmenite. When sieved and panned from creeks, these grains often settle at the very bottom with other heavies, hugging the corners of gold pan or the central lobe of batiste. Their rounded but blocky shape, rather than splintered or slaty, can help separate them from detrital debris. When multiple indicators show up together, especially pyrope, ilmenite, and chromite, your odds of nearby diamond presence increase substantially. In professional sampling campaigns, ratios of these minerals are often mapped in grids to triangulate pipe locations. A single grain isn't proof, but a cluster appearing within a tight radius signals transport from a nearby eroded source. However, context matters. These minerals can survive transport, but they don't travel far in nature. A common rule is 1 kilometer of downstream drift per millimeter of grain size. If you're finding them consistently in one area but not upstream, that tells you the source lies somewhere nearby, often within a 500 to 800 meter window. And yet, indicators can deceive. Some regions have similar mineral suites from unrelated rocks. That's why the next layer of testing isn't just about presence. It's about performance. Does the stone you think might be a diamond respond like one under field conditions? That's where we shift from what the eye sees to what the stone tells us under stress, thermal, magnetic, and UV response. Out in the field, there's no luxury of a lab. Only a limited window of daylight, a pocket full of tools, and the pressure to make fast, defensible calls. So when a suspected diamond shows up amid a swirl of pyrope garnets and magnetic heavies, it's time to escalate testing beyond the visual. The next layer of confidence comes from how the candidate reacts to heat, magnetism, and ultraviolet light, each revealing clues the eye can't. The fastest and most decisive tool is a thermal conductivity tester. Commercially available diamond pens, often costing under $100, send a mild heat pulse through the stone and measure how quickly it dissipates. Diamonds, due to their extreme thermal conductivity, register almost instantly with a beep or flashing indicator. Glass, quartz, and most fakes absorb the heat and respond slowly or not at all. Moissanite, an often used diamond simulant, can sometimes pass this test too, so it's critical not to treat this result as final. UV fluorescence adds nuance. Many natural diamonds fluoresce blue under long-wave UV light, a trait that once devalued stones but now helps differentiate them from glass and most synthetics. However, not all diamonds fluoresce, and some synthetics have been engineered to mimic this trait. What's important is a combination. If a stone shows adamantine luster, octahedral habit, and thermal conductivity consistent with diamond, but fluoresces with an unusual color, like yellow, orange, or green, you're likely dealing with simulant or lab-grown material. Magnetism provides a separate branch of testing, more relevant to the minerals around the diamond than the stone itself. Sweep a neodymium magnet over your concentrate. Ilmenite may shift subtly, magnetite will jump. While diamonds themselves are not magnetic, this sweep confirms the indicator suite and helps separate false visual hits from credible geological context. A lone shiny stone in sterile sediment isn't worth your time, but one nestled in a pan with responsive black grains? That's a different story. Another useful check is the weight to volume feel. If not a formal specific gravity test, then a quick comparison against known materials. Hold the suspect stone alongside a quartz chunk of similar size. If the candidate feels significantly heavier, it's worth preserving for later water displacement testing, which can confirm a specific gravity near 3.52, a strong confirmation for diamond. Still, these tests aren't infallible. Thermal pens can misread in cold weather or if the stone is wet. UV lighting is affected by the stone's clarity and surface grime. And even moissanite can imitate enough traits to fool most portable field tests, which is why, when a candidate stone passes its battery but still feels off, The prudent step is to record, isolate, and sample again, then return with a clean field protocol. At this point, we're no longer chasing a fluke glint in a stream. We're building a profile. But with every escalation comes a new layer of complexity. What happens when the tests all lean positive, but something doesn't add up? That's the moment we confront a very real trap. Stones that behave like diamonds, but aren't. It's a pitfall that derails even experienced field collectors. The stone that checks nearly every box, right up until the final costly moment. It tests positive on the thermal pen, shows no facet doubling under the loupe, feels dense in the hand, and even fluoresces blue under UV. But when it finally reaches a qualified gemologist or lab, the truth emerges. It's moissanite, or worse, zircon. Both can masquerade as diamond in the field, and each has led to false claims, wasted resources, and misplaced excitement. Take moissanite first. Originally a rare mineral discovered in meteorite impact sites, synthetic moissanite is now commercially produced and widely available. Its hardness is high, around 9.25 on the Mohs scale, and its thermal conductivity is comparable to diamond, making it notoriously difficult to distinguish using only a heat probe. But there's a flaw in its disguise. Moissanite is birefringent. When viewed under 10x magnification, its internal structure splits light into two paths, causing facet edges to appear doubled. It's subtle, but unmistakable once seen. Zircon poses a different challenge. Natural zircon can be colorless, glassy, and dense, close to diamond at a specific gravity of 4.6, even higher than diamond itself. Some specimens, particularly those with minimal inclusions, exhibit strong luster and can fool collectors unfamiliar with its behavior. But zircon is almost always singly refractive and tends to display a high degree of dispersion, those rainbow fire flashes that seem too vivid in rough form. Under UV, zircon often fluoresces yellow or orange, a major distinction from the typical blue of many natural diamonds. Then there's a lead glass trap, high-index synthetic glass doped with barium or lead to simulate diamond's luster. These fakes often contain small air bubbles, curved fracture lines, or conchoidal surfaces that give them away upon close inspection. Yet in wet gravel, surrounded by opaque minerals and glinting under sunlight, they can easily pass an initial screen. That's why field tests must never stand alone. They are filters, not proof. When a suspect stone raises questions after field testing, the smart move isn't to discard it. It's to establish a control set. Test known samples, quartz, glass, zircon, synthetic moissanite, under the same conditions and compare behaviors side by side. Thermal response, weight in hand, luster under sunlight, loupe inspection for facet doubling. All should be repeatable. If your candidate diverges from known fakes in multiple dimensions, it climbs the ladder of credibility. Still, false positives are a rite of passage. Many serious collectors report dozens of hopeful tests for every confirmed diamond, but each one sharpens the process. And sometimes the mistake isn't in being wrong. It's in being too quick to give up. Because the stone you toss aside as synthetic today might, under a new light or angle, reveal a subtle feature that changes everything. That's exactly what happened in the case we're about to examine, where a discarded glass shard turned out not just to be real, but to originate from a pipe type no one expected. It sat in a tray marked rejects for over a year. Angular, translucent, slightly frosted. What looked like a jagged shard of bottle glass had been tested once in the field, flagged as synthetic based on UV fluorescence, and forgotten. But during a reevaluation of sample concentrates from a dry riverbed in Central Australia, it caught a geologist's eye. The habit was too regular, the weight too distinct, and when retested with lab-grade tools, the result didn't just confirm it was a natural diamond. It revealed a source that rewrote the map. The original misidentification hinged on a false positive from a portable UV test. The stone had glowed faint greenish blue under long-wave UV, a fluorescent signature that raised suspicion of synthetic origin, especially given its proximity to quartz veins and a known feldspar intrusion. But field UV lights often distort color perception. especially on cloudy days or when batteries weaken. Under calibrated conditions in the gemological lab, the fluorescence shifted to a pale blue consistent with type Ia diamonds, a natural form with aggregated nitrogen impurities. Further imaging revealed internal strain lines and metallic inclusions, tiny blebs of perovskite and chromite, common to diamonds formed in high-pressure mantle conditions. This alone established the stone's natural status. But the surprise came from the chemistry of its mineral inclusions. These weren't consistent with typical kimberlite-hosted diamonds. Instead, trace element analysis pointed to lamproite, a far rarer, and until recently, largely dismissed host rock in the region. This mattered more than most realized. Kimberlite pipes have been the focus of decades of exploration across southern Africa and parts of Australia, but lamproite was considered less predictable, more geochemically complex, and sparsely mapped. The few known diamondiferous lamproite pipes, like the famous Argyle deposit, were outliers. Until now, the stone, 3.8 carats uncut, appraised over $10,000 in rough condition due to its size and octahedral integrity. But more importantly, it reframed an entire field campaign. Follow-up sampling revealed a trail of pyrope garnets with unusual chromium signatures and altered olivine, classic companions to lamproitic weathering. What was once dismissed as an overwashed gravel field became a new prospecting hotspot. This case underscored a brutal lesson. Initial test results, especially in the field, are suggestive but not conclusive. Field tools are screening mechanisms, not final arbiters. What matters is context, pattern recognition, and persistence. One misread fluorescence signal nearly buried a $10,000 stone, and the geologic lead it carried with it. Now the game changed. If diamonds could emerge from previously dismissed terrains, what other samples in past concentrates have been misread? And more critically, how can we structure testing so we don't make that mistake again? To answer that, we need to look at what labs can do that field tests can't, and where expert verification draws a true line between synthetic mimic and natural treasure. What separates suspicion from certainty is often a microscope and a thin section. While field tools offer valuable first impressions, only a lab can reveal the inner structure, inclusion chemistry, and growth patterns that confirm a diamond's identity and natural origin. And in a market flooded with synthetics and high-quality simulants, these differences have become non-negotiable. When a stone reaches a recognized gemological lab, such as the GIA, Gemological Institute of America, SSCF, Swiss Gemological Institute, or NGTC, National Gemstone Testing Center in China, it undergoes a suite of standardized tests that go far beyond handheld tools. One of the most telling is infrared spectroscopy. This test categorizes a diamond by type based on nitrogen content and aggregation. Type Ia diamonds, containing aggregated nitrogen, are overwhelmingly natural. Type IIB diamonds, though rarer, can also be natural but are more susceptible to misidentification if lab-grown variants aren't ruled out. In the case of our reclassified lamproite origin diamond, spectroscopy confirmed a type Ia signature, but the real clincher came from inclusions. Using laser Raman spectroscopy and scanning electron microscopy (SEM), technicians identified chromite, olivine, and perovskite in inclusions that were fully enclosed, meaning they were trapped during crystal growth, not implanted later. This inclusion assemblage is diagnostic of high-pressure formation in the Earth's mantle and cannot be replicated in surface-level synthetic processes. Strain patterns visible under cross-polarized light also tell a story. Natural diamonds often display complex internal strain, zoning, twinning, or graining that reflects their geological journey. These features create interference colors and distortions absent in most synthetic stones, which grow under more controlled, uniform conditions. Lab-grown diamonds, especially those produced by chemical vapor deposition (CVD), typically show tabular growth layers and metallic inclusions from the reactor environment, which contrast starkly with the irregular growth features of natural stones. Fluorescence, previously a point of confusion in the field, is resolved here with precise measurements. Labs don't just observe color. They quantify the strength, wavelength, and response under both long-wave and short-wave UV. A faint bluish glow in the field becomes a recorded, calibrated trait. If the stone glows differently under the two wavelengths or shows phosphorescence, lingering glow after the light is removed, it can further indicate synthetic origin or natural history. All these traits, spectral type, inclusion makeup, strain behavior, and fluorescence profile, converge to form a fingerprint, and once matched against known natural signatures, they don't just verify a diamond's authenticity, they may trace it to a specific deposit type, sometimes even a regional origin. That's not just academically interesting. In the trade, provenance can move a diamond from $1,500 per CT to over $5,000 per CT, especially when linked to conflict-free, certified, or historically significant sources. But lab verification is slow, expensive, and not feasible for every field find. So where should the line be drawn between holding a stone for certification or writing it off? The answer lies in mapping repeatability and proximity, a tactic that converts one-off hits into credible patterns. Before investing in lab work, the next step is to grid the terrain and prove the find wasn't luck. Because even a verified diamond means little if it came from nowhere. The goal now is to test the land itself and see if the pattern repeats. One diamond does not make a deposit, but 2, 3, or more within a predictable radius start to define a system. That's why the next logical step after a confirmed lab result isn't celebration, it's grid sampling. Establishing repeatability is how prospectors separate a fluke from a find worth staking, developing, or selling. And the process is anything but guesswork. The core principle is spatial discipline. A single high-value recovery, especially from an alluvial setting, tells you the terrain upstream might contain a primary or secondary source. But unless you map and sample methodically, you'll never know if the stone was an isolated traveler or part of a dispersal fan. Gridding eliminates that ambiguity. A practical grid begins with center point, usually the GPS location of the first confirmed stone. From there, a systematic sweep in all directions begins, typically in 100-meter intervals. At each node, you sample a consistent volume of material, often 10 to 20 liters of sediment, focusing on heavy mineral concentrates. Each sample is labeled, sieve using number 20 and number 40 mesh, and the concentrates pan down to recover any dense material. Pyrope, garnet, chromite, ilmenite, and ideally, additional diamond candidates. The rule of thumb is that if indicator minerals increase toward a direction, you're moving closer to the source. If they thin out or vanish, you're drifting downstream or off-trend. More telling than a second diamond is a bullseye of indicator minerals, concentrated directly above or adjacent to the original find. That pattern suggests erosion from a localized bedrock source, possibly a weathered pipe or dike. Repeatability also includes cross-validation of tools. Each positive sample should be tested with the same field methods as before: thermal probe, UV response, weight comparison, but it's essential to test them blind without bias. Stones should be coded and tested without knowing their grid origin to reduce confirmation bias. Only after these field results are recorded do you recheck them against known samples and lab-confirmed stones. Data from a strong grid campaign can justify sending multiple samples for lab verification, or even bringing in geophysical surveys. Resistivity imaging, magnetic mapping, and soil geochemistry can then layer over the grid to triangulate subsurface structures. Some of the most productive secondary diamond sites were found not by stumbling over crystals, but by following a tightly executed grid that revealed an overlooked lamproite or kimberlite intrusion. But timing matters. Access to the land, whether public or private, often comes with constraints. In many regions, sample collection, especially of mechanical or involving disturbance to stream beds, requires permits. These can take weeks to secure and are seasonally restricted in flood-prone areas. That clock pressure, especially in remote areas, can force choices. Test wider with less depth or concentrate narrowly with greater intensity. Repeatability is the proof of concept phase. It doesn't just build a geological case. It establishes legal and financial leverage. A single diamond is a curiosity. A repeatable pattern, grid-mapped and sample-verified, is evidence of a potential economic asset. And in many jurisdictions, that distinction determines whether you can file a claim, seek partners, or market the data. Still, not all terrains yield equally. Even with perfect sampling, some areas are just barren. So, how do you know where this method is most effective and where you're wasting your time? That's the next filter. Understanding the regional geology and terrain types where diamond prospecting is viable isn't optional. It's mission critical. You can run perfect grids in the wrong place for a decade and never see a single carat. That's the blunt reality of diamond prospecting. Terrain governs success. The method works only where deep-time geology intersects with surface transport, and not all landscapes qualify. Knowing where to apply this workflow is what separates productive campaigns from wasted effort. Start with the cratons. These are the ancient, stable cores of continental crust, thick, cold, and often billions of years old. Every economically significant diamond deposit known today is either on or adjacent to craton. The Kapval Craton in southern Africa, the Canadian Shield, the São Francisco Craton in Brazil, the Siberian Craton, and the Yilgarn Craton in Australia all share this common denominator. Why? Because these thick crustal zones are the only places where kimberlite and lamproite magmas have had access to deep mantle conditions long enough for diamond formation. But not every craton surface hosts diamonds. The next filter is magmatic. Kimberlite and lamproite pipes are the delivery vehicles, and their distribution is patchy. Kimberlite is more common and tends to form caret-shaped pipes with consistent geophysical signature. Lamproite is rarer, chemically distinct and less predictable in shape, often forming diatremes or dikes. The key is historical mapping. If you're working within a known kimberlite field or on the margins of an underexplored craton, your odds rise sharply. Equally important is erosion history. You don't need exposed pipes. You need their sedimentary residue in reachable terrain. This means alluvial systems, paleochannels, or erosional windows where diamonds and indicator minerals have been liberated from weathered volcanic rock and transported into gravel beds. These transport systems can stretch several kilometers from the source, but the heaviest material, including diamonds, settles quickly. That's why inside bends, terraces, and overbank deposits are critical. However, in tropical zones with intense weathering, like much of West Africa or parts of the Amazon, lateritic soils can obscure alluvial channels and hide pipes under iron-rich crust. In these cases, soil geochemistry and airborne geophysics often precede field sampling. The field method still works, but only after terrain analysis reveals where residuals might concentrate. Conversely, applying this method in geologically young terrains, like volcanic arcs, mid-ocean ridges, or areas dominated by sedimentary basins, will yield nothing. No kimberlite, no diamonds. Similarly, terrains dominated by glacial transport, e.g. much of northern Europe, require modified strategies. Glacial erratics can carry indicator minerals hundreds of kilometers, making local sampling less reliable without first accounting for ice flow paths. And then there's human contamination. Urban and post-industrial landscapes often yield glass shards, ceramics, and slag with misleading visual or thermal traits. These environments produce the highest false positive rates, and unless you're deliberately testing urban runoff or tailings for recovery, they're best avoided. Ultimately, this method thrives where ancient geologic structure meets accessible surface transport, old terrains, eroded pipes, sediment traps. But once you confirmed your region is viable, a new challenge emerges. What if you're not looking for diamond but jade, opal, or another valuable mineral that mimics diamond indicators? That's when even the best trained eye can be led astray, unless you understand the geologic imposters hiding in plain sight. From a distance, it gleamed with the same muted intensity, a semi-translucent chunk, pale green in some light, milky in others. To the untrained eye, it mirrored the subtle luster of a raw diamond, But as the field tests began to contradict each other, the truth became clear. It wasn't a diamond at all. It was nephrite, a form of jade, misread due to its mass, color, and context. And in other cases, it's opal, hydrated silica with just enough heft and glow to fool a thermal test. These are the geological imposters, and they can mislead even well-executed sampling campaigns if you're not tuned to their environments. Jade, for instance, is a chameleon. Nephrite occurs in serpentinized terrains, often near altered ultramafic rocks. It's associated with minerals like actinolite, epidote, chlorite, and magnetite, all of which can also appear in diamond indicator suites, especially if weathered. That overlap creates confusion. Nephrite's specific gravity, ranging from 2.9 to 3.0, is close enough to feel heavy in hand compared to quartz or feldspar, but light compared to diamond. The difference is subtle, especially in wet or muddy field conditions. More importantly, nephrite can be tough, fibrous, and luster in a way that resembles some low-grade diamond rough. But the fibrous texture gives it away under magnification. Instead of clean faces or stepped crystal surfaces, nephrite shows a felted, interlocking texture. The true giveaway is its behavior under thermal testing. Nephrite absorbs heat slowly and registers far below diamond on a conductivity pen. However, if the pen tip is misaligned or the stone is wet, false readings can occur. Jadeite, the rarer and more valuable form of jade, also appears in subduction-related terrains. In places like Guatemala, Myanmar, and parts of Japan, jadeite nodules weather out into streams where they can co-occur with serpentinized material. While rarely mistaken for diamond due to its color, often rich green or lavender, white jadeite can, in poor lighting, be misclassified, especially when its dense structure gives it unusual heft. Opal presents a different challenge. Found in volcanic and sedimentary terrains, like the Andamuka Fields in Australia or the Virgin Valley in Nevada, common opal potch can appear glassy, colorless, and oddly lustrous. It may show play of color or not. Because it's hydrated silica, its weight can vary, and it often registers poorly on thermal conductivity, but just well enough to confuse a rush test. Unlike diamond, opal often shows internal crazing or moisture loss fractures, and under UV, it can fluoresce in whites, greens, or oranges, depending on impurities. The common thread across these imposters is geologic mismatch. Diamonds appear in cratonic, volcanic conduit systems, kimberlite and lamproite. Jade appears in subduction or metamorphic zones. Opal forms in sedimentary or volcanic weathering contexts. Knowing which minerals belong to which system allows field workers to filter not just by what a stone looks like, but whether it even makes sense to be there. That said, misidentifying a jade or opal as diamond might not be a complete loss. High-quality nephrite or jadeite can fetch $50 to $2,000 per kilogram or more, depending on color and translucency. Precious opal, if found with strong play of color and no fractures, can command up to $500 to $5,000 per CT when cut. The key is not to discard unusual stones too early, but to reroute their identification path once geologic context contradicts your first assumption. But what if the stone is real, the terrain is right, and you've hit on something valuable? Before you move it, share it, or dig deeper, there's one crucial step left: checking the legal ground beneath your boots. A single misstep can void a valuable discovery, not in the pan, but on paper. Because even if the diamond is real, the terrain promising and the samples compelling, if you're collecting or testing without proper permission, the find could legally belong to someone else or be deemed illegally obtained. In many regions, mineral rights don't follow common sense. Land ownership and subsurface rights are often decoupled, and prospecting without awareness of that separation is a fast track to forfeiture or legal penalties. Access law varies wildly by country, state, and even by district. In parts of Canada and Australia, for instance, public lands may permit recreational sampling under prospectors' licenses, but those rights are limited by volume, intent, and disturbance level. In the U.S. Bureau of Land Management, BLM, lands can often be sampled under casual use. But once you identify a potentially economic mineral, like diamond, you're required to file a claim and follow regulatory pathways before further testing or extraction. Ignoring that step makes any subsequent find unprovable and potentially forfeit to the state. In protected areas, such as designated wilderness zones, reserves, or indigenous lands, sampling is often outright prohibited, regardless of method or intent. Even using hand tools in a dry creek can violate environmental statutes or cultural heritage protections. In Brazil and other South American countries, illegal sampling in indigenous zones has led to arrests and equipment seizures, particularly for high-value minerals like diamonds and gold. Permits range in complexity. For small-scale exploration, many jurisdictions offer reconnaissance or temporary sampling permits, usually requiring submission of coordinates, volume limits, and assurance of minimal environmental impact. These permits don't grant extraction rights, but they do legalize collection and testing, allowing you to preserve chain of custody and prove provenance if a valuable stone emerges. That provenance matters. Without documented permission, even a certified diamond may be difficult to sell or export. Auction houses and buyers increasingly demand proof of legal origin, not just to comply with conflict mineral regulations, but to avoid reputational risk. A high-quality rough diamond without a paper trail will be devalued, no matter how flawless its form. If you're working on private land, permission from the landowner is essential, but it's not always enough. Many mineral rights in developed regions were split from surface rights decades ago. That means a landowner may not legally own the minerals beneath. A title search or regional mineral registry check is the only way to confirm. In areas like the UK, all gold and silver belong to the Crown by default, and diamond finds are scrutinized under similar historic laws. Digital tools help. Many regions now offer GIS-based mineral rights maps or online portals where you can file sampling intentions, locate active claims, or check surface access status. Carrying printed permission documents or screenshots is advisable, especially when operating in remote areas where enforcement may be erratic but severe when encountered. In short, a find isn't real until it's legal. And in diamond prospecting, where values quickly escalate and competition is fierce, the rules aren't suggestions, they're protection. So with permits in place, tools calibrated, and stones ready for retesting, the next move is to lock in a method for proof. Because value doesn't come from a single result, it comes from patterns that repeat. And proving that pattern begins with a plan. The moment you find a promising stone, the instinct is to escalate. But escalation without structure turns discovery into noise. To transform a single candidate into a defendable, valuable asset, you need verification through repeatability. That means a plan built on grid logic, process control, and data integrity. One that ensures any future find can be linked, confirmed, and, if necessary, defended. The foundation of this plan is grid sampling, but not just for locating more stones. Grid work becomes a scaffolding for confidence. Each sample site must be tagged, recorded with GPS, and assigned a unique identifier. That ID follows the sample from raw gravel to concentrate to test result. If you find a diamond candidate at point D3, you must be able to trace it back to the exact volume of sediment, data collection, and test results, thermal, UV, weight, and field context. The next step is controlled resampling. That means return to points that yielded positive results and collecting again. Same volume, same tools, same method. If the first hit was real, repetition will either reinforce the trend or reveal it as a fluke. The more times a sample site produces similar indicator suites, pyrope garnet, ilmenite, chromite, the more confident you can be that a nearby source is feeding those minerals. Where possible, integrate independent observers or third-party verification. In prospecting partnerships, this adds credibility. Even if you're working solo, keeping detailed logs and timestamp photos creates a defensible record. Include images of your concentrate pans, sample collection process, and results. These will matter if you seek partners, file a claim, or approach labs for formal testing. When it escalates to lab testing, not after the first visual hit, but once multiple field positives from a tight cluster confirm a trend, At that point, submitting 3 to 5 candidate stones, ideally from different but adjacent sample nodes, allows labs to detect pattern consistency. If all 5 are confirmed diamonds and the mineral inclusion suggests a single source lithology, your case for a viable deposit becomes exponentially stronger. As part of this verification plan, incorporate specific gravity testing. A simple setup using a jeweler's scale and water displacement allows you to calculate density with good precision. True diamond will land near 3.52 G/cm superscript 3, while most imposters fall short. If a sample passes thermal conductivity, UV profile, and lands within plus or minus 0.03 of the diamond gravity benchmark, you've narrowed the odds of error dramatically. Another field verifiable trait is optical behavior, specifically birefringence. Under a 10x loop, rotate the stone and observe facet edges. If they appear doubled or smeared, it's likely moissanite or zircon. Diamonds are singly refractive, and clean edges stay sharp as the stone moves. Incorporating this test into your record sheet for each sample sharpens both your skill and your dataset. The goal is not just to collect stones, but to build a body of evidence. Verified stones with traceable grid origin, consistent indicator mineral support, specific gravity logs, thermal response, and optical results form the basis of a reportable discovery. And if the stones align in trend and terrain, the case becomes strong enough to attract buyers, partners, or even institutional interest. But before you take that step, you need to understand what's on the table. Because even verified rough diamonds don't all command the same price. And understanding how those prices are determined could be the difference between selling too soon or holding for something far more lucrative. You found it, tested it, verified it. But now comes the most misunderstood phase, valuing it. Because rough diamonds don't carry a fixed worth. They carry potential. That potential is shaped not only by size or clarity, but by what the market sees in the stone. Cut yield, color stability, inclusion type, and most crucially, provenance. Getting the value right starts with knowing which variables the industry truly pays for, and which ones buyers use to lowball. The first and most obvious factor is carat weight. Rough diamonds under 0.5 carats typically sell in bulk lots, often for $15 to $40 per carat depending on clarity. Between 0.5 and 2 carats, individual stone value begins to diverge. Stones over 2 carats with intact octahedral habit can fetch $200 to $600 per carat even in uncut form. If the stone shows few visible inclusions and promising proportions for cutting, those figures climb sharply. Clarity matters, but not in the same way as in finished gems. What cutters look for are the types and locations of inclusions. Black carbon spots near the surface reduce yield, while small pinpoint inclusions near the center may disappear during faceting. A rough diamond with minimal surface-reaching inclusions can command double the price of a similar-sized stone with poor integrity, even if both test identically. Color, or more accurately, lack of it, is another lever. Most rough diamonds are lightly tinted yellow, brown, or gray. Colorless rough is rare and commands a premium. However, very strong coloration, especially pinks, greens, or blues, can elevate a stone's value dramatically if the color is natural and stable. Lab testing is often needed to confirm this, especially with greens, which are frequently radiation-induced and unstable during cutting. Then comes shape and habit. Octahedral crystals, those with sharp, well-formed faces, are prized because they offer predictable cutting potential. Flattened dodecahedrons or irregular shapes reduce yield, making them less valuable even at similar weight. Rounded or resorbed stones, those partially melted during volcanic ascent, are common but require expert assessment to determine what's salvageable. Provenance plays a hidden but growing role. Stones confirmed from known conflict-free zones or from regions with active traceability initiatives, like Canada or Botswana, can sell for more, especially when buyers want to avoid reputational risk. If your verified stones come from a previously undocumented but traceable source, they carry novelty value, especially if part of a potential new field. But that value only materializes if the paperwork matches the geology, Sample logs, permits, and lab reports all matter. So what's the floor and ceiling? For small, low-clarity industrial rough, prices can be as low as $10 per carat. For high-integrity octahedral stones above 2 carats, market rates start around $500 per CT and may rise to $2,000 to $3,000 per CT if cutting potential and clarity align. Exceptional stones, especially in rare colors or from high-profile finds, may enter the $5,000 to $15,000 per CT range uncut. However, the riskiest moment is the first buyer offer. Many buyers will test with thermal pens only and immediately attempt to lump stones into low-value categories, citing risk or uncertainty as justification. That's why bringing a GI or comparable lab report, even for just one stone in a group, can leverage the whole lot upward. Verified rough tend to elevate surrounding stones through association. Still, even with the right data and reports, stones are often undervalued in the field. That leads to a different kind of trap, not misidentifying the stone, but misunderstanding the negotiation. Because the next real challenge isn't geological, it's financial. And if you don't know how buyers work, you could watch a 5-figure stone get sold for pocket change. It's the silent loss most prospectors never realize. You've done the work, found the stone, verified it, even got a lab report, and yet, when it comes time to sell, the offer barely covers your costs. The reason? You walked into a value game without understanding the buyer's playbook. Because when it comes to rough diamonds, price isn't just about quality. It's about position, power, and presentation. Buyers, especially mobile buyers or small-scale intermediaries, know that field finders often lack cutting expertise, network access, or time. They bank on urgency, using phrases like industrial quality, low demand right now, or risk of breakage to pressure fast decisions. One of the most common tricks is to test a stone with a basic thermal pen, nod once, then downplay it. Could be diamond, but without clarity, it's low grade. That phrasing creates the illusion of validation while setting a low price ceiling. Another tactic is association devaluation. If your verified diamond is presented alongside unverified or ambiguous stones, buyers will offer a group rate, often underpricing confirmed stone to absorb risk on the rest. The solution? Always separate knowns from unknowns, with documentation to back the difference. A single GI report with carat weight inclusion map and type classification can shift offers by a factor of 5. Then there's the testing charade. A buyer might use a UV lamp to highlight fluorescence and suggest the stone is synthetic, even when the type of fluorescence is common in natural diamonds. Others may press for moisture on the stone to obscure the thermal test. In either case, the strategy is to seed doubt. Your best defense isn't confrontation. It's repeatable test data, including video or photo documentation of thermal response, specific gravity setups, and optical inspection results, all linked to the sample's chain of custody. Timing matters too. Stones tested and sold during gem show circuits or auction seasons fetch higher rates, especially if buyers know others are competing. The inverse is also true. Private, off-cycle offers tend to underprice, capitalizing on your isolation from the broader market. That's why holding until you have multiple stones or a reportable pattern from a grid can boost collective value more than selling solo. But for those unwilling to navigate the trade directly, there are alternatives. Some prospectors choose to license the discovery, not the stones. If your samples show a repeatable pattern in a viable terrain, that data can be packaged and sold to exploration companies or private buyers with capital to develop the site. This route values the information, not just the mineral, and often commands a higher upfront premium without requiring you to extract more. Ultimately, the path you choose, sell rough, cut and grade, or license the lead, should match your capacity and risk tolerance. The important thing is recognizing that in this world, knowledge outvalues raw material. What you've tested, mapped, and verified becomes a foundation, not just for one sale, but for an informed, repeatable process. And that's where we close. From a glint in a gravel bed mistaken for glass, to a stone verified as a natural diamond from a lamproite source, to a structured field campaign and lab-confirmed provenance. This wasn't just a story of mineral identification. It was a process of pattern recognition, methodical verification, and strategic positioning. Because in the end, the difference between stepping over a fortune and holding one isn't just about what you find. It's about how you prove it.